Welcome to this video with an example of analyzing determinate structures. This is one of several videos in a short course on equilibrium posted at terje's Toolbox, a website that contains notes, examples, and algorithms for structural analysis. The truss considered in this video is slightly more complex than in the previous video. This is a statically determinate truss with 7 members and 2 external loads. It is possible to start the analysis of this truss by considering equilibrium at joint E. However, let us in this case follow standard procedure, which means finding the reaction forces first. Sum of moments about A or C, plus horizontal and vertical equilibrium, gives the reaction forces shown in this figure. Notice that the reaction at point A is a downwards acting force because the external loads try to topple the entire truss about point C. Next, we consider equilibrium at point E again. We mark the joint as a solid point in step 1. The 200 kN external load is known, while the 2 member forces are unknown. In step 2 of the procedure, we put the 200 kN force down on paper first. Next, we play around with the inclined and horizontal force directions in order to create a closed force polygon. Triangle equalities, as we did in the previous video, gives the force values shown here. Notice the triangle shown below, which is taken from the truss, with lengths in meters, compared with the triangle that forms a closed force polygon. One message to take away from this drawing is that we simply do triangle equalities for the sake of geometry. We do not need to have the sides of the geometric triangle be actual members of the truss. We just want to have a geometrical shape that compares with the shape of the force polygon. With arrow directions taken from the closed force polygon, we are able to tell that the inclined member is in compression and the horizontal member is in tension, because this arrow is pulling at the joint. Next, we move to joint C, which is on the bottom right-hand side, where the pin support is located. If we scroll up to the figure of the truss, we see that this is an interesting joint, because 5 forces act on it. 2 are reaction forces, shown here, and 1 is the 245.8 kN force that we just determined. Scrolling down to the joint equilibrium, we start with step 1. The 3 known forces are shown in red. The 2 unknown forces are shown with question marks. We arbitrarily decided to put the known forces down on paper in the order 510, 300, and 245.8. We then arbitrarily start with the inclined force direction followed by the horizontal force direction in order to close the force polygon. The result is marked with the pink color. It is not immediately clear which triangle equalities can help us determine the value of the 2 unknown forces. It turns out that it is best to bring into the picture the force polygon that previously gave us 245.8 kN. That is done in the upper left corner of this new force polygon. As a result, we know this 200 kN vertical value and the total 442.86 horizontal value. As a result, this 310 vertical value is trivial. In turn, that gives the 221.43 horizontal value at the bottom and the 380.96 force in the inclined member. Finally, the total horizontal value 442.86 is subtracted the 221.43 value in order to find the force in the horizontal member. As usual, we summarize the results in step 3, which here shows all force values, including directions. Next, we move to joint B. This is an unusually simple joint, because the known force in the horizontal member is directly matched by the unknown force in the adjacent horizontal member. There is no force in the vertical member. Next, we move to joint A on the very left-hand side. At this point, only the force in the inclined member is unknown. The force polygon is a triangle in this case, and we have now seen this type of shape several times in this short course. The result is a 380.96 kN tensile force in the inclined member. All forces are now determined. However, we proceed by checking equilibrium at joint D at the top. 4 forces appear there, 2 of them horizontal. The closed force polygon shown here confirms that the joint is in equilibrium. Thanks for watching this video. Please visit terje's Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.